So today I'm going to review, not sure how much, but I'm gonna try to review probably for around 2 hours the pictures that I took from the books. So I think I read around 14 books about hardware, microarchitecture, and a couple of them were from operational systems. I did another list with a bunch of operational system books as well, which I think I'm gonna try to read, but it's just like a lot of them. And I'm gonna start reading again the like this is one of the books that I thought it was really nice uh, about the operational systems. Probably the best book that I've read so far about operational systems is understanding the Linux kernel. So I read this and I'm gonna read it again, I think, and then start reading the other ones. But what I want to do is just there's also other Moodle lectures here that I took the slides from the some of the courses that I did, which is just playlists on YouTube. But I'm not really sure if I'm gonna be able to review this today, obviously, because there's a lot of stuff. And to be honest, so I think the first I'm gonna go in alphabetical order here. So in the order that it is here, and then each one that I finish, I'm gonna put on this folder just to remember. And I'm not gonna. The other ones that I also did was about networking as well, but it's on another folder. So I think I'm gonna try eventually to go over all the resources I have here, which is just a lot. So I'm gonna start with this one, which is about circuits, and this one's about circuits. I didn't pay too much attention on some of them because I was reading like several different books at the same time. So it's very hard to concentrate on these ones because they are like more far away from what I'm actually gonna use. So like I'm less interested on them. So I think I'm gonna try to go over kind of fast each picture because there's also a lot of pictures that I took. And then if I have some time later, because I'm not really sure how long I'm gonna spend here, but I think I'm gonna try to do 2 hours for this stuff, then take a break, and then I'm in the process of creating this other project that because one of the things that on Godot that was is still kind of annoying me is that the way that they design Godot is more for a different kind of user, I think. So they design Godot with the like for someone that is probably not going to spend too much time on the engine and who wants more to develop games fast and is going to use GDScript to do it. And I really don't like GDScript. And based on the way that I'm trying to do things anyway, which I already built at the beginning of an IDE scene, or just using Godot. So, like for my case, it doesn't make sense to use GDScript. So what I was thinking about for a long time is to like how to simplify everything, and also the project manager as well. So like I'm trying to create a system that allows me to just build everything from C++. And then if I need a scripting language, I'm probably gonna try to do it from Python and just use the OS class from Godot to run programs from Python. And obviously I'm not really sure how I'm gonna do this, but I think eventually I'm gonna try to use CPython to extend to be able to like merge Python with C and C++ and to be able to use it on Godot. So I decided to create an entire new folder, which I just copied from this previous one to create this project here because like the changes that I make, that I'm trying to make, I think are going to be fundamental to the way that the engine works. And if I get to this part, then I'm going to explain what the stuff that I'm trying to do. But it's basically just change the main setup function and I change the whole engine so that I can build everything from C++. And I don't need, and eventually I'm going to try to remove this stuff related to GDScript as well. But I still want to have the old version so that if I need to use the editor, then I can I can use the old compiled version, and just move this stuff from this other one to there. And Celerity is a name that ChatGPT suggested. Is some stuff that I don't remember, but I thought it sounds nice. So what I'm gonna try to do is to continue developing that project now, and that project is gonna also have another version probably of Godot as well that I'm gonna use to compile and to use that as the base engine to export, like for the export system, because the exported project is just the engine, the compile executable, which is the engine executable, with the resources from the project embedded into the executable. Either that or the resources as a package on the same folder as the engine executable. So what I'm going to try to do is just find a way to automate everything from C++, just create executable, like an optimized build of the executable based on the C++ code that I build like the entire scene on C++. And then use this optimized compile version of the engine to build the project automatically from C++. And then probably use that on the IDE scene to use a process like so that I can increase the iteration, the development speed. That's the main priority, obviously. So I'm gonna try to go very fast over all of these images here, see if I can remember. I think this one is about the like transistors or yeah, transistors for analog systems. So systems that convert analog signals to digital signals. Also, I'm gonna open the. It's probably another thing that I'm gonna do as well, but I think I'm gonna do this after. So probably the best idea is to review these images. Then after this, I wrote down a bunch of keywords. I'm probably gonna have to go over all of them as well. So this stuff here is related to, like some of the stuff is gonna, it was related to analog systems, and these other ones are related to sound. It's kind of like similar because obviously to convert sound to digital, it's kind of like similar thing. And there was a name here. There's this specific thing that I remember about on the books, that on the transistor there's a name for a threshold. Yeah, the triode region. That's the name. So this is the only thing that's like stood out for me on this that I kind of remember from the book. Is that there you have a region on the transistor on the gate where there is some nuance on the signal, because obviously it's going to be based on capacitance, and you can get into physics. It's going to get very complicated because of the different models there, but yeah, it's basically working based on the voltage and based on the structure of the material is going to determine how the voltage changes, like how the structure of the voltage is going to change based on the gates, based on the geometry of the gates. Oh, there's also a book that I read some time ago about neurochemistry or something like that. Now, one thing that I like a lot about neurochemistry books is the images. They're very clear. And I also took a bunch of pictures from the book. So maybe I'll go over that one as well, but I'm not really sure. Maybe it's a good idea to go over now because it's kind of like it's interesting to see the contrast, because it's like very similar, but it's obviously not the same. But the principle is very similar. On the neurochemistry is going to be action potentials on the, I think it's sodium potassium channels that are gonna determine like the fluctuation or like the signal. And on the transistor is gonna be the silicon and I think it's oxygen. The silicon, and there's the other. There are other variations of the gates, but it's gonna be based on the magnitude of the voltage, the capacitance, and yeah, the barrier or like the relationship between the different materials. think MOS stands for metal oxidized semiconductor or something like that. And you have PMOS and NMOS. Yeah, MOSFETs, and they call it a device on the books. Metal oxides, metal oxides, semiconductor. So you have yeah, N type and P type, and they are the inverse of each other. So one of them is considered to be on when you put the voltage, and the other one is considered to be off when you put the voltage, and it's because of the difference on the materials. And then you have this CMOS. CMOS I wrote down here from other multiple lectures, but I think on the books they talk about MOS. But I think it's just like the same thing. Just like a slight difference on the materials. Insulator is the oxide. And as far as I understand now, the way that the clock works is going to be based on capacitancy. So a capacitor that it holds charge for a temporary amount. So it's like if you're pouring water on a tank that has a sink, uh, the capacitor is gonna be the not sink is the container where you put the water in. So like the moment you stop putting the water, if you didn't have the tank, you would cut the flow right away. But because you have the tank, then you have this extra amount, and that's the capacity, as far as I understand. And it's based on like putting the insulator in the middle of the thing that conducts the voltage. So that capacity creates the clock cycles. I think it's based on the yeah. So this I remember from Ben Eater lectures. So like you have the flow, you have the voltage on top, then you have the capacity, and then you have a drain on some other parts of the circuit. And then the clock is the capacitor, and yeah, based on that relationship of the logic that activates the drain and the capacitor, you're gonna have the frequency of the clock. That frequency is gonna change the states of the machine, and the machine is a finite state machine. So it's like a predefined transitions of states based on combinational logic. Another thing that is kind of hard is when reading these books is that I wasn't really sure. Like, kind of took a bunch of pictures from every picture that I was seeing, and then I skipped a couple of them, but I think I took like most of them. And it's because it's kind of hard to know like what exactly is going to be a good picture to take. So I think a lot of these pictures are going to be kind of redundant, and also because I read so many books, so like I had to go really fast through all of them. There's so much shit to learn. Probably the honor Mutlu stuff's gonna be more interesting. Should probably go faster through this. Yeah, this is the triode region that they were talking about. So as far as I understand, triode region is the region. Maybe I should use ChatGPT actually for this as well. Yeah, I think that's a good idea. I'm gonna ask ChatGPT questions as I review this. But from what I remember, the triode region is gonna be like this connection here between. So like this on top is the gate, and the other parts are the like source and drain. So the connection between them here is where it's gonna be like it's not gonna be black and white. So like the smaller it gets, the more complicated it becomes, because obviously you're changing the. So on the standard model, they say you're changing like the flow of electrons from one part to the other. But from the other model, which is the ether model, which I think that's more accurate, it's just you're changing the pressure mediation. So something that the Ken Wheeler talks about, the Theoria Hypothesis, the YouTube channel guy, is that the smaller the space, the higher the capacity. And it's because the capacity or the energy is the ether, which by its definition is the lack of space, because it exists on a non-Cartesian plane. So the reason why you have electricity is because of the geometrical shape of the like molecules or atoms of the material that create this pressure mediation of the material. So the difference in pressure mediation of the two materials creates the semiconductor, which allows you to manipulate that voltage by connecting the structure, the geometrical structure, with other materials, which would be like the source of the voltage. So the way that I think about it now is like computation is going to be a complex pattern, complex geometry, that when interacting with a specific kind of other geometry creates or changes the pressure mediation of the geometry, and the flow of that structure creates computation, which is just like the relationship between the logic gate is going to create the informational system, which is computation. So like this stuff is relevant to producing the gates when you're going to produce, because obviously you have to like have quality of service and like make sure that's going to work, obviously. So the smaller it gets, the more complicated it becomes to not have noise on these things. And I don't remember if like analog systems they use. I do think, from what I remember, it is different, that there are different kinds of gates you can use for analog systems. And probably they take advantage of this thing. But I don't remember really well. I'm gonna ask ChatGPT. What is a triode region? So this is talking about the how the like the function of pressure mediation between the two. As obviously like on the voltage and on the drain is like fixed numbers. So I think that's usually the number is gonna be 3 voltages for the source, and then 0 for the drain. So obviously it's not gonna be like go from 3 to 0 directly out of nowhere. So I think it passes through this function here, according to their studies, when you turn the transistor on or off. And this is called latency, like the time that it takes for the voltage to travel along the circuit. And this is also important for the timing analysis, because obviously I think that the timing has to be based on the longest path of the circuitry, because you need to make sure that the rise of edge of the clock synchronizes with the logic for the circuit. I forgot to put, no, put yeah, so this is probably the function, or how the pressure mediation, but according to them, is going to be the electrons, but I think it's pressure mediation. It's going to change based on the voltage you apply to the gate. One thing that I remember that I used to think, it's kind of confusing when you see the circuitries, is that when you see circuits, you're gonna see the resistor or resistance drawing based on a specific place. But obviously now I think that it works more across the whole material. It's kind of like I think the better way to think about it is like something moving through water. Like something moving through water is different than something moving through air. It's because of the resistance of the whole thing. So for voltage is the same thing, I think. Is like the because and nothing is moving according to Ken Wheeler, I think. But and that's what I think as well, is that like you're changing the pressure mediation of the field. So it's like a wave kind of impact where it's not like the current is moving from one place to the other, but you're changing the nature of the field itself, and that creates the sensation of something moving. And this is across the material, so the resistance is not on a specific point of the thing. It's like a continuum over the material. And then obviously the resistance is going to be used to calculate on the formulas to calculate the current and the voltage and stuff, other stuff like that. Because I don't, like, obviously I'm not sure if this formula here is correct. And I don't remember a lot of the formulas, but I do know that there's going to be this, I think the I is for the current, yeah. So I is current, the V is voltage, and the R is resistance, and C is going to be capacitance, I think. Yeah, oxide capacity. And these amplifiers I remember from the DRAM lectures, Ono Mutler lectures. or I think it's on the flash memory lessons. So you have amplifier on the bottom of the bank, the memory bank. Then based on the signal, like when you read the row, you like fuck up the signal of the row. Then you use that on the amplifier to like amplify the signal because it's a very small signal on the capacitance. Then it amplifies with the amplifier to get a clear one or zero, and then the amplifier has like a circuitry that goes back to the row to refresh the row. Because when you read the row on a flash memory, it's gonna fuck up the data. By reading, you change the values, so you have to refresh later. I'm pretty sure there's gonna be slides on the owner stuff. Yeah, so this is probably used for calculations of like because obviously you're gonna have optimizations on the voltage as well. Obviously you always want to use less energy to achieve the same result. So in order to have these calculations, you need to create these formulas to see like how it's gonna be, what is gonna be the impact of a certain voltage on the circuitry. How low can you go and the latency, bandwidth, stuff like that. I think I'm gonna try to go faster over this. Transconductance. Yeah, I think to truly understand these books, you have to spend a lot more time on each one. And I think it's kind of in the fact that to be honest, it's probably a lot better to just watch videos. I do remember this one was very. I think this the other ones about the transistors and the physics level were more like dense. I think this one specifically had a bunch of different circuits here, and this is kind of the problem because then you have to spend a bunch of time like trying to understand how this is gonna create the logic gates and what does it mean. And obviously didn't do that. I just went very fast. So yeah, the good thing is about this is getting the keywords because then it becomes easier to search for videos on YouTube. This is kind of interesting as well. So like there is some one of the biggest problems with analog to digital is the interference, like the noise of the signal. So I do remember that there are some points where they had pictures or showed there is an amplifier on the circuit, but I don't remember the nuances very well. Amplifying stages. Well, there's another thing that I remember reading a lot on these books, like seeing a lot, but I don't remember exactly what it is. Based on the name, you can kind of infer what it is, but I'm gonna ask you the. I'm just gonna go very fast. There's a bunch of different pictures. I think I'm gonna try to get to the hardware part as fast as possible. I'm just gonna skip over a bunch of this. Just trying to see if there isn't anything that, any keyword or something like that, that it might be interesting to search later. Oh yeah, so obviously, like makes sense that analog signals are gonna, the analog to digital is gonna use amplifiers, obviously. And I think that that's the part that is related to the filtering process as well. Because you're gonna amplify the signals you want and not the other ones. But I don't remember anything about the nuances. Okay, so it looks like this is the end of this one. Turn on phenomenal. Wow. But this is just the voltage at which is gonna, the gate's gonna open, let's say. So it's gonna become a 1. And it's based on these constants and this other relationship between the materials. Work functions. Yeah, so I'm gonna close this one. I'm gonna go to the other one. still think it's worth it to go over all of them because I do think that there are some of the pictures might be interesting. Like, or have some stuff that is different. At this part, I still have to because like the thing is, it's still kind of confusing to me, like the sequence of steps very clearly. You know, I didn't understand. So basically, you guys, as far as I understand right now, the way that it works is that you have this giant thing of silicon that they slice to create these wafers, and then they shoot light patterns, or they also use a gas, and that's the part that I think the name is physical vapor decomposition or something like that. I wrote down here some parts. So there's chemical vapor, chemical. I think is deposition is something like that. Physical. Maybe it's PVD. Tell me if I didn't write here. I was pretty sure I did write here somewhere. Somewhere. I think it's physical vapor deposition. The name of the process. So basically, they either shoots. So the chemical one is with gases, as far as I understand. They put this wafer on a chamber, and then they throw a hot gas with some material, and they also have a vacuum tube. And then based on the interaction of that gas with the wafer, it leaves a thin layer. But the part that I don't understand is either this process or the other process is like kind of shooting physical things, like physical particles, small particles on the thing, and also having the vacuum tube, and then you create the thin layer on the material. And I think that's what creates like the base for creating for later on creating the gaps between the material with the photoresist or whatever the name of the thing is that you shoot the lights to create the pattern. But the part of the pattern that is the one that I don't understand very well. Like I don't have a very clear picture still on my mind of like what exactly are the process, and it's just like very complex as well, I think. But I think that this is like this relationship between the wafer and the thin layer is kind of confusing to me. I think it's physical vapor deposition. Mice is the name of the one of the simulators that they use to create the pattern of the gates. Yeah, so this part here I think is the part of the physical or chemical vapor deposition. I think you should create this thin layer of copper. I think. I'm not sure. Yeah, I think that's the how it works. So the process of so you have the wafer, then you create the thin layer, which is gonna be the other material. Then you on the when you shoot the light, it creates like the pattern because it creates the gates on the thing. And I think that's according to GPT is gonna be like there's other processes that clean up the thing. It's kind of like cleaning up the not sure how to say that in English, like unwanted like materials from like to make the pattern cleaner, let's say. And I think that on the other part they're gonna put another material to work as the wires, so that when you put the voltage, it creates the based on the geometry of the transistors, it's gonna create the computation. So step 6.3 just 6.4. So it's different parts than the one that I was thinking about. It's probably this here. So the chemical or vapor are adding the material that is gonna create the wiring, I think. According to ChatGPT, which obviously could be wrong. So I was thinking more that would be on the other one. I think layer of copper. So I think this is the process of transforming the silicon into that SO2 form. So basically changing the material. So I think you put this as gas here on a hot wafer, and then it's gonna create the layer on top of the silicon. Then on some other part of the process is gonna create the gates by shooting the light. So according to ChatGPT, this battery effect is just the how changing the voltage is gonna change the threshold voltage of the transistor. So it's like not a binary thing. I'm not sure if that's a good analogy, but it would be like when you try to move a tank that has some amount of water, like obviously the more water you put on the tank, the harder it becomes to move. Because I think it's basically the same kind of thing here. Once you put the voltage on the gate, if it has this battery effect, it's going to become harder to keep the gate open with the same amount of voltage. This picture here explains very well what I was thinking. So it is the way that I was thinking about. So I have this initial material. This is already with the oxygen, but I think before you have the process where you put the gas on the hot wafer and then it creates this thing here. Then you add this photoresist layer on top of it, and then when you use this mask and you shoot the light, it creates the gate pattern. I think that's how it works. And then the edge removes the part in the middle here. And then I think you remove the photoresist. Yeah. So basically the first step is gonna be to add the thing that's I think it depends, like it's gonna depend on the kind of transistor, I think. Which material is gonna be negative and which one is gonna be positive. I'm gonna ask this as well. On this situation here, which one is the negative one? Yeah, so it does depends on which kind of transistor it is. The operational position. So this would be the NOT gate on CMOS. I think the voltage is here and the drain is here.